Hello, today we're going to talk about section 9.8. This is about galvanic, which are also called voltaic cells, and about electrolytic cells.
So I think it's worth our time to review what redox reactions are and kind of what we need to do with those before we get into voltaic and electrolytic cells. Redox reactions. Redox is short for reduction and oxidation, and I always use the acronym OIL-RIG. Oxidation is losing electrons, reduction is gaining electrons. So if you have a reaction like solid copper is forming copper 2+ ions and releasing those 2 electrons, that's an example of oxidation because the copper is losing its electrons. An example of reduction would be something like chlorine, chlorine attracting 2 electrons to form 2 chloride ions. There we go. Just trying to make it work together. All right, so the chlorine here is gaining 2 electrons, so this is a reduction reaction. These are called half reactions because they show the electrons. Now, in reality, these can't occur on their own. They have to occur together. You have to have at least one oxidation and at least one reduction reaction together because the electrons have to go somewhere. So you can put these 2 together in what we call the overall reaction. So if you were to add these 2 up, notice how I chose ones where the electrons are the same. So you can just add them together. The solid copper can react with the chlorine gas to form copper 2+ ions and 2 chloride ions. And I took out the electrons because they were the same, because there is a transfer of electrons, we just can't see it in the overall reaction. So again, this is an oxidation half reaction, this one is a reduction half reaction, and this would be the overall reaction if I put the 2 together. Okay, let's go ahead and review oxidation numbers because that can help us track where the electrons are going in more complex reactions or if they don't give you the half reactions. So oxidation numbers, there's a handful of rules involving them. If you have an element in its standard state, then its oxidation number is 0, so something like sodium metal or chlorine gas. Those are in their standard state, their oxidation numbers are 0. If you have a metal in a compound, like calcium chloride, the metal in that compound will have the same oxidation number as its charge, which in this case, calcium has a charge of 2 plus, so its oxidation number is +2. We always write oxidation numbers with the sign and then the magnitude. Then we would look at oxygen in compounds. So oxygen in a compound will be -2 unless it's a peroxide. So an example of that would be water. Oxygen's in that water molecule, its oxidation number is -2. A peroxide like hydrogen peroxide, and then it's -1. Hydrogen in compounds is always +1. An example of that would be in the water molecule, that hydrogen has a +1 oxidation state. The exception to that would be if it's a metal hydride, something like NaH, then the hydrogen would be -1. That does not come up often at all. Okay. And then finally, anything else you would have to make it add up. All the oxidation numbers add up to the charge on the compound. So let me give you an example of that. If I have like Na2SO4. Sodium is a metal in the compound, so its oxidation number is the same as the charge, which is +1. Oxygen in a compound, it's not a peroxide, so it's -2. The overall charge on the compound was 0, so all of the oxidation numbers have to add up to 0. I don't know what the sulfur is just by looking. I have to figure it out. There's 2 positives from the sodium and 8 negatives from the oxygen, so the sulfur has to be +6 to get everything to add up to 0. And so that's how you would figure out any other oxidation number. Now, how do we use oxidation numbers? You would look to see from the reactants to the product side. If the oxidation number on the product side increases, it goes from 0 to positive 1 or something. If it increases, then that thing was oxidized over the course of the reaction. If you have a different reaction, the reactant is going to the products. If that oxidation state is going down at all, then we say that it was reduced over the course of the reaction. Okay, I already showed you kind of a simple example of oxidation and reduction half reactions and how to write an overall reaction. But let's look at one that's a little bit more complicated. If I have something like sodium metal, and when it forms its ion, sodium ion, it will release 1 electron. If I have oxygen gas, if it gains 4 electrons, I can make 2 oxygen ions, 2 oxides. Now these ones, the electrons don't match up. So if I wanted to like pair those 2 half reactions together, the oxidation and the reduction half reactions, I need to make sure that the electrons are the same. So I would have to multiply this reaction by 4. So I would have 4 sodium ions, 4 sodium atoms leads 4 sodium ions and 4 electrons. Now my electrons are the same on both sides. I can add up to make my overall redox reaction. I have 4 sodiums and my oxygen gas making 4 sodium ions and 2 oxides. So now I know that the reaction is balanced overall because the electrons are the same. So you need to make sure that when you're putting those reactions together, you have the same number of electrons for both. Okay, now let's get into voltaic cells. They're also called galvanic cells. I will typically call it a voltaic cell. The biggest thing you need to know about voltaic cell is that it's spontaneous. So, and that means it's thermodynamically favorable. It has a delta G value that's negative, and it will have an overall cell potential that is positive. Okay. You don't have to add any outside power source. So when you are creating a diagram or you're looking at a diagram of a voltaic cell, you'll see that typically it's attached to something, but that's just going to measure the voltage produced by the electrons traveling through that wire. It will not provide power. We're going to look at electrolytic cells probably in section 10. And electrolytic cells will have a power source of some kind. The electrolytic cells are non-spontaneous because they require an input of work from that power source. And electrolytic cells will have a delta G that is positive and a cell potential that is negative. So let's look at the different parts of the voltaic cell here. You will typically have these metal electrodes. One of them will be the anode, one of them will be the cathode, and they will be connected by a wire, and usually there'll be some kind of measuring tool, a voltmeter, a multimeter, something like that. The metal electrodes will be submerged in a solution containing the same kind of element, just in its ionic form. So when it's zinc sulfate, that is a soluble compound. So it's actually forming zinc 2+ ions and sulfate ions. And so that's what we need. We need the solid and the ionic form. We have the solid copper, and we will have ionic copper and sulfate ions. We tend to use the same ion, anion on both sides as well. Then, in addition to connecting with the wire, you will also see the two connected with what's called a salt bridge. That could look a lot of different ways. So it could be a bridge of salt. Sometimes it's in like a glass tube packed with a salt, like potassium chloride. It should be a soluble salt. Sometimes it's sodium chloride, sometimes it's sodium nitrate, but it needs to be a completely soluble salt. And Sometimes, instead of seeing a salt bridge like this, you'll see that the containers are just butted up against each other like this, and we'll have some kind of porous barrier between the two. So the ions can travel across that porous barrier without the need of a specific salt bridge. So don't be alarmed if your image doesn't look exactly like this. All right. Let's talk about the reactions that are happening in a voltaic or galvanic cell, and then we'll look at the specific movement of species in this next. So we measure the potential of a particular element using what's called a reduction potential. So when we're looking at things like copper and zinc, which were the two elements that we were looking at in the previous slide, we always write them as reduction reactions, and that's just convention. They could have chose to put all of them as oxidation, but they have to be the same format for us to compare them. So they chose reduction. I don't know who they were, but they chose reduction. So that means reduction is gaining electrons. So all of the reduction potentials will be written as a reduction half reaction. So the zinc. So these are my two reduction half reactions. Now, they will give you some kind of what's called reduction potential. And what happens is they compared this to a standard electrode. This is typically a hydrogen electrode. And when they compared that, they saw the difference in potential of the copper to the hydrogen. And in this case, the copper was 0.34 difference from the hydrogen standard. And then the zinc, when that was compared, its difference was negative 0.76. And so these are measured in volts, and these are called the reduction potentials. All right. This helps us to figure out when we have two half reactions, it helps us to figure out which one is going to stay as reduction and which one is going to flip to be oxidized. The one that is smaller, when you're comparing the reduction potentials, the one that is smaller will have to flip. Okay, the larger the value, the more likely it is to be reduced. Smaller the value, less likely to be reduced. So whichever one's smaller will be flipped. So I'm going to rewrite this reaction. Zinc goes to zinc ions plus those two electrons. When I flip the reaction, I will flip the sign on the cell potential. Now this is important. I'm going to go ahead and cross that out because I used it. We always talk about adding up the electrons or adding up the reactions as long as the electrons are matching. It works in this case, which is great. But if they didn't match, you would have to multiply the whole reaction, just like we did before. When you multiply, you can multiply by 2 or by 4 or by whatever, as long as the electrons are becoming the same for both the redox or both of the half reactions. When you do that, when you multiply a whole reaction, you do not multiply the cell potential. Don't do it. The number of atoms that are actually reacting in any particular given situation does not affect the potential difference. Once you get the electrons the same, then you can add them all up together. So I have the copper ions plus the solid zinc, forming zinc ions plus the solid copper. And you can add up the potentials at that point. So your overall cell potential is 1.10 volts. Okay, now this should be a positive number, always, because you flipped the one that was smaller. Now this is only true when we're doing a voltaic or galvanic cell. When you're connecting for an electrolytic cell, you can make the reaction go in a different direction than it wants to by adding a power source. So this is what is happening to the reaction in our diagram that we looked at on the previous slide. The copper ions are turning into solid copper, and the zinc atoms, the solid zinc atoms, are dissolving into zinc ions. So the copper was reduced over the course of the reaction, and the zinc was oxidized. Okay, so here's kind of an expanded diagram from the one we looked at before. We have our half reactions, and we know that the zinc is going to be flipped so that it's oxidized, and then we can find our overall reaction. Because the zinc was being oxidized, we call whichever side is being oxidized, we call that the anode. So the zinc, the piece of zinc metal is the anode, and this is our oxidation half cell. It's a half cell. Okay, the whole thing is a cell, each part is a half cell. The copper, because it has the larger value, is reduced. We call that the cathode. And so this whole thing is called the cathode, or the reduction half cell. All right. Now let's talk about what is moving around in this cell when it's reacting. So the electrons are going to travel from the anode to the cathode. Electrons travel from the anode to the cathode. So if we think about it, let me rewrite this zinc reaction so it looks like oxidation. Zinc goes to 2 electrons plus the zinc 2 plus ions. I flipped that. So the zinc loses its electrons, releases them. It loses its electrons, they go up the wire, and they travel around to the copper. Well, copper needs to gain electrons, so that's why the electrons travel in that direction. You will be asked to label diagrams like this in order for the movement of electrons. Now, when this happens, you wind up with extra electrons over here. The cell doesn't like that because then the charge isn't balanced. So what happens, because you have these extra negative ions, is that whatever your salt is, it will split up into ions. The positive ion goes toward the cathode. The way that I like to remember it is that cations travel toward the cathode. The anode, because the zinc was losing its electrons, you'll wind up with extra positive charges over here. So to balance out that charge difference, the negative ion from your salt will travel toward the anode. The anion travels toward the anode. Okay. If you don't have a salt bridge or a porous membrane, the cell just won't work because it will transfer like 1 electron, realize the charge is balanced, and stop. The charge has to stay balanced, so the salt bridge works to balance the charge. Again, you will be asked to label which way the anions are traveling and which way the cations are traveling in the salt bridge. Okay. So that's for your wire and for your salt bridge. Now you also need to think about what's happening with the ions in the reaction itself. The copper ions are becoming solid copper. So these copper ions that are here in the solution are going to turn into solid copper, and it kind of gloms on to the cathode itself. So the size of the cathode will increase as the reaction proceeds. Now at the anode side, the zinc metal will be turning into zinc ions. So these pieces of the zinc will be turning into additional zinc ions. So this one actually will get smaller as the reaction proceeds. So we have 2 half reactions. We want to write the balanced overall reaction. Whichever one is smaller will give us the thing that we need to flip. So it's this one, the sodium one. We need to flip that around. And we also need to multiply it by 2 because we need to make the electrons match. So I will say there's 2 solid sodiums forming 2 sodium ions and 2 electrons. And our cell potential will change signs, positive 2.71. Remember, you don't multiply by 2 like we did everything else. The cell potential, the magnitude stays the same. So our overall reaction, you will have the magnesium 2 plus ions, the 2 solid sodiums, the 2 sodium ions, and the magnesium solid. If we were to calculate the voltage for the cell, you want to add up the positive 2.71 with the negative 2.37, and you get a 0.34. It is a positive value, and it's in volts. So that's how you can check to make sure that it is correct, to make sure it's positive. Now the anode is the one that is oxidized, so this is our half reaction for the anode. And then at the cathode, it is For our cathode, it is this magnesium half reaction right here, because reduction is gaining electrons. And as the reaction is going, what happens to the anode? Remember, anode is oxidation. So the sodium metal will decrease in size. It dissolves into ions. And for the cathode is reduction. And so at the cathode is actually getting bigger because you're creating more solid magnesium, so it's increasing in size.